Okay, so how is everyone today? Good? All right. So, last time we were talking about substitution in the context of integrals. So let's do another one of those before we move on to something new. So today's the, what? 14? Okay, so here's one. So integral from 0 to 8 of the cube root of w multiplied by the square root of w to 4/3 plus 9 dw. Okay. So we want to evaluate this integral. And so recall that integral is, in the end, related to area. So does this look like, this, one of the first things that you can ask yourself, is this like one of the easy ones? Like, is this somehow like a circle or some other shape that you know? It's not. All right. So then, since it's not like a circle or something, we should then ask, well, if we're going to use the fundamental theorem of calculus, then is this one of the three antiderivatives that we know? It's not. Okay, so then, just as a reminder, the way the procedure goes is you ask, is this a known antiderivative? Okay, and at the risk of being repetitive, I'm going to write them down again. So the known antiderivatives are antiderivative of x to exponent n dx when n is not -1. That antiderivative, we refer to that one as the power rule. So it's x to n plus 1 over n plus 1 plus a constant. In the specific case when the exponent is -1, we can still do it, but we just can't use the power rule. So what is the antiderivative of x to -1? dx? Which one is it? Yeah, yes, x. So you could also write it as 1 over x dx, like so. But then what's the antiderivative? Very good. Oh, is that what you said? I just couldn't hear you. So log absolute x there. Then the last one is the exponential case. The antiderivative of the exponential is the exponential. And just as a reminder, the exponential one kind of is a stand-in for a family of such ones, including, for example, this one. What's the antiderivative of, say, 5 to x dx? Mm-hmm. That's right. And then plus a constant. So in fact, there's nothing special about 5. The only thing that's necessary is that you need the base to be a constant which is positive and not 1. So in particular, this green thing would be just as true if we replaced 5 with e, right? The reason why it works is because what is the natural log of the natural number? 1. Okay, good. So, is it a known antiderivative? Is this one a known antiderivative? It is not. No, because it's not in the list. The next step is, can you do some algebra to sort of, you know, work some algebra magic to get it to be something that we know? Is there something we can do?
Yeah.
Okay, what?
Where the dot is, the multiplication dot, you can split those in half.
What do you mean split in half?
I guess one of the ones in the homework is like, if you do 0 to 8 cube root W and then 0 to 8 of the other square root W to the fourth, and it's equal to 9.
Oh, you definitely cannot do this. So if I understood you correctly, you suggested something like this. So f of x, g of x, dx, something that looks like that, and then splitting it on the product like this. So saying that it's equal to this.
Yeah, maybe it's subtraction. There's one operation to do that. But
Yeah, you can do it with add and subtract.
okay,
Yeah, but definitely not with multiply.
Okay, I'm not
So, you know, I'll retroactively change this to a plus, and then it's right. But that's not what this one is. Okay, so all right, let's consider this carefully. So, how about let's consider something like the following: 4 multiplied by x plus I don't know, plus 3. So the 4 can, in a sense, get inside the parentheses. So specifically, it is like you could take this 4 and the multiply, and you can give a copy of it to the x and another copy of it to the 3. Right? So it's like you get a multiply by 4, you get a multiply by 4, everybody gets a multiply by 4. So this would be 4 times x plus 4 times 3. And what's the name for that? Doing this? It's a D word. Distribution, right? So specifically, this is distribution of product over sum. That's the name for what that is. And the reason why I'm bringing that up is because a similar looking kind of thing happens to derivative, for example, and antiderivative for that matter. So like the derivative of, you know, f of x plus g of x. Now this is not the same kind of thing, but it looks similar, right? Because the rule is you know, because that's a sum, you know, you get a derivative and you get a derivative, right? So derivative also distributes across sum. Distribution across sum is called additivity. So this is like this. So this is, you know, distribution of derivative over sum. So does derivative distribute across product just like that? No, it's got something more interesting, right? It does the product rule. Remember, we talked about that with a rectangle changing sides, changing area. All right. So distribution of product over sum. So now I'm going to take to make another comment. I'm going to take this 4, and I'm going to take the x and the 3, and do something slightly different. What if I say, instead of x plus 3, I say x multiply 3? And what if instead of saying multiply by 4, I say exponent 4? So like this. So now, in this class, probably different than your, possibly different than your previous math courses, I always write the dot when I mean multiply, just to remind you that it's a thing. But I don't go so far as to do the same thing with the exponents, because I find that to be a little bit tedious to look at. But exponent has a punctuation. What's its punctuation? Caret, right? So this is, you could write this, you know, with complete punctuation like this. And so now, is there a rule here that does this? And the answer is, yeah, actually. You can take this caret 4 and you can give it to the 3 and you can give it to the x. It works in the same way. So this is, this becomes x caret 4 and then multiply 3 caret 4. And normally, you know, you'd write it like this. X to 4, 3 to 4. So that's another rule. So just like this one is called the distribution of product over sum, what's this one?
Distribution of power.
Yeah, the distribution of caret over product. The distribution of exponentiation over product. So this is a distribution of caret over product. Now here's where it goes wrong. Is that okay? So we've got product over sum. That's good. We've got exponent over product. That's good. The problem comes when you get to the following. What if I take the x and the 3, so the x and the 3, and I still do exponent. I still do that. But instead of making it product, I make it sum. Now does it distribute? It does not, right? So what I'm about to write is incorrect. So if you're going to write it, be sure and write down that it is incorrect. So the reason, I promise there's a reason I'm getting this seemingly far off the beaten trail, like this, x to 4 plus 3 to 4, as if the 4 could just go to the individual items. So this doesn't work. So no, caret does not distribute over sum. So here's the deal, is that with the exception of this derivative business, there's 3 arithmetic operations on the page, and they are of increasing complexity. We've got add, and then we have multiply. Now, multiply is really just repeated addition. Like when you write 10x, that literally means x plus x plus x plus x plus x plus x plus x 10 times. That's what it means. Similarly, after product, we have caret. And caret is just a repeated product. So like when you write, say, x to 4, that means x times x times x times x. That's what it means. So 4 x's all together in a product. So 1, 2, 3. And there are other ones, but we just don't talk about them at this level. You know, it just keeps going. So this pair distributes. There's a distribution rule for this one. Product does distribute over sum. And this pair distributes. caret distributes over product. But you can't take these two. There's not a distribution that involves this one and that one. It's too big of a jump. It doesn't work. It's not the same. So one of the reasons why I selected this exercise, and one of the reasons why I'm getting us so far off the beaten trail here, seemingly, is that on an exercise similar to this, I saw numerous attempts to do something like the following. So please consider, is this a correct thing or is it not? So the square root of, say, x squared plus 9 equal to the square root of x squared plus the square root of 9. So I'm asking a question. Is that a legitimate thing to have done? Okay, why not?
You're leaving out the middle of the, like when you expand x plus 3, like, it's not the same. It just doesn't give you the right answer.
Okay, all right.
You have to add it. You have to do the operations under the square root because they're together.
Okay, well let me ask this one.
It's not a community property.
What about if I change it to this? X squared multiply 9 equal square root x squared multiply square root 9? Is that one true? Why or why not? It has something to do with what we did on the left side.
The multiplication with the caret, but instead of the caret, it's really a square root.
Well, okay, yes, I agree. But square root, doesn't that correspond to some fractional exponent? It is. It's half. So really, radical is just a sort of a cute way to write caret 1/2. So what two operations are at play here? We have caret 1/2 and add. Do they distribute like that? They do not. This one is not correct. Is this one correct? It is. That one is right. That one is right because, so this one is false. And this one is true. The reason in the end is, you need to recall that the square root of t means, or another way to write it anyway, is t to 1/2. So that top one like this with the plus is talking about. You could rewrite it as this: x squared and then plus 9, and then if you like caret 1/2. So the question is can we distribute that caret over the sum? And the answer is no, you can't. You cannot do it. No distribution is possible. Whereas for this one, x squared product 9 caret 1/2. Can you do a distribution here? You can. Okay. So I bring this up because, well, in the end, there's nothing special about this summer. I mean, literally every time I teach calculus, this happens. That students try to distribute, in the end, try to distribute caret over sum. but it's not a thing. You can't do that. Any questions? So we were trying to answer this question. Is this some simple thing like a circle? No, it's not. If we were going to use the fundamental theorem of calculus, is this a known antiderivative? No, it's not. Is there something algebraic we can do to make it work out better? Nah, because the only thing we might do is like try to distribute the square root somehow, but it doesn't distribute over sum. So if there's nothing algebraic to do, what's the next step? Yeah, we need to check a substitution. Substitution. And I'll just copy that integral down here. Now, I admit fully that, you know, I'm really sort of hammering home some points here. And of course, this exercise could be done far more rapidly if I wasn't taking us so far afield for these other matters. So, can we do a substitution? All right. So remember that the beginning of wisdom is calling things by their proper name. So substitution, that's really a short name for the true name of this thing. What's it called? A variable differential substitution, right? So that reflects the fact that there's kind of two bits to this, two pieces. It's we want to see if we can undo the chain rule. So that means that we want to find a thing, which we'll call u, and we also want to find the derivative of u. We want to find both of those things. All right. So to that end, I'm going to rewrite this integral in a slightly more calculus-friendly manner. So specifically, for example, how will I rewrite the cube root of w? Good. Because typically, where calculus is concerned, w to 1/3 is a more friendly representation of cube root. Similarly, I'll write this as w to 4/3 plus 9, and then to exponent half, and then dw. All right. So we want to find, we want to make a variable differential substitution. So what do you want to make the variable? The one in the parentheses, okay? That's generally a good idea. So we'll try u is w to 4/3 plus 9. So anytime that you have something that looks like this, you know, parentheses, and you've got a sum in there and some exponent, especially if that exponent is not an integer, it's usually a good idea to try to make that the variable. Okay, so then the differential, du dw, well, the derivative of that would be 4/3 w, and then the new exponent would be 4/3 minus 1. That's the power rule for derivatives. And then what's 4/3 minus 1? 1/3, right? Because 1 is 3/3. So 4/3 minus 3/3 is 1/3. And at any rate, I'm starting to get warm fuzzies about this line of reasoning. Why? Starting to feel good about it. Right, because we have that w to 1/3 hanging out right there. So the fact that it showed up here, that's good. All right, then we need to solve for du. So du is 4/3 w to 1/3 dw. All right, so what's currently on offer is we're saying that, okay, this is going to be the variable. And then we have to account for these bits in the differential. So I see that the w to 1/3 match up. That's good. I see that the dw's match up. That's good. But we've got this extra 4/3. So what? So like what I'm saying right now is that this is, you know, we like that one's good, we like that one's good, but at the present time this is extra. Yeah, we want to get it on the other side. So division by 4/3 is the same as multiplication by 3/4. So then doing that, this would be 3/4 du is w to 1/3 dw. Okay, so that's good. So then this differential part, 3/4 du, will substitute for this. So I'm going to go ahead and, so there's one more bit, one more aspect of this integral that involves w's. So we took care of the variable part, we took care of the differential part, but there's one more aspect of this that involves w's. What aspect? The 0 to 8, right? Because this integration is occurring over the interval of w's ranging from 0 to 8. Right? That's what these mean. So 0 less or equal to w less or equal to 8. So the 0 and the 8 have to do with the w. So if we're going to switch things, if we're going to do a variable differential substitution, I'm going to go ahead and switch the 0 and the 8 to from w's to u's. Now, that being said, of course, we talked about that other way to go about doing it, and if you want to do it that way, that's fine too. That is to say, where you leave these in terms of the original variable and then go back to the original variable before you evaluate. That's fine too. But I'm going to change these now. So u evaluated at 0. U evaluated at 0 would be, well, 0 to 4/3 plus 9. And then what's 0 to 4/3? 0. So this would just be 9. And then 0, sorry, u when w is 8 would be 8 to 4/3 plus 9, which raises the question, what's 8 to 4/3? Also, you know, it's 16, but you know, that just raises the question a little more like, okay, why is it 16, right? Well, furthermore, to understand all of the exercises we're going to do in the class, you've got to understand how to do this without the aid of a calculator. So let's remember how to do that. So as an aside, the definition of x to m over n. So when you want to evaluate this, this actually means, it's a short way to write x to 1 over n to m. That's what it actually means. Right? Because when you have iterated exponents, what do you do with them? You multiply them, right? So what's 1 over n times m? Well, it's m over n. All right? So, strictly speaking, this is when m and n have no common factors. So like 4 and 3 are in that situation. So as a result, we can say, well, okay, 8 to 4/3. What does that mean? The other way, the other order. So it's 8 to 1/3. You do that bit first, and then raise that to exponent 4. So, yeah? That's right. So fractional exponent third means cube root. So what's the cube root of 8? 2, right? Because 2 times 2 is 4, times another 2 is 8. So this is really 2 to exponent 4. And then what's 2 to exponent 4? Well, it's 16. So that's why 8 to the 4/3 is 16. All right, good. So that's, a peculiar way to write 16, and 16 plus 9 is 25. All right. So what we're saying is that these numbers are going to replace these numbers. All right. So as a result, the new integral is 9 to 25. And then the variable, u to half, and then 3/4 du. Any question getting to here? All right, so now, again, the integral, and for that matter, the antiderivative, because we're using the fundamental theorem, is homogeneous, which means that this constant 3/4, it's kind of just, the process is blind to it. You can, mentally just factor it out and leave it as a factor. So I'll just ignore it for a moment and ask, okay, now that we've significantly altered the corresponding antiderivative, is this one of the antiderivatives that we know? It is. Which one is it? The power rule. With which exponent? 1/2. All right. So that means that this would be 3/4 multiplied by u to, well, the new exponent would be 1/2 plus 1. And then divide by 1/2 plus 1. And then this evaluated from 9 to 25. All right. So because we're going to evaluate some things, I'm going to algebraically simplify this before I start to plug stuff in. Okay, 1/2 plus 1 is what? 3/2. So this would be 3/4 plus u to exponent 3/2, and then we're dividing by 3/2, and then evaluating all that from 9 to 25. Okay, now division by 3/2, we could simplify that. How can we simplify it? Multiply by 2/3, right? Because division by a fraction is the same as multiplication by its reciprocal. So this could be rewritten as 3/4 multiplied by 2/3 multiplied by u to 1/2 from 9 to 25. The 3's cancel, the 2 and the 4 become just 1/2. So this would be 1/2 multiplied by u to 1/2, and then 9 to 25. I'm sorry? Oh, I don't know. That's just a mistake. the exponent should be 3/2 all the way through. Somehow from here to there, I don't know what happened. It became 1/2, but it should be 3/2. So this is about as simple as I can make it. Right? I've sort of like put off evaluating as far as I could. But now it can't be put off any further. We talked about a trick last time. I'll remind you of it. That is that if we have something that looks like this, k multiplied by f of x, and then we're going to evaluate from x is 13 to x is 26. So if we're going to do that, then, well, this is k multiplied by f of 26 minus k multiplied by f of 13. But do you notice that both of those terms have a common k in them? So we could factor that out and do it like this. F of 26 minus f of 13. So that's the common practice when you do this. So what I mean is I'm going to evaluate this now, but notice that it has this constant multiplier 1/2. So I'm going to leave it factored out and write that this is half multiplied by 25 to 3/2 minus 9 to 3/2, like so. So that's just leaving the half factored out. Okay, which now that we had this aside up here about fractional exponents, we can do this. So for example, what's 9 to 3/2? 27. And how'd you do it? Right. So you do fractional exponent 1/2 first, so square root of 9, which is 3. And then 3 to exponent 3 is 27, as you say. So, you know, what we said there was, well, this will be 9 to half and then cubed, like that. And that ends up being 27. So 25, well, we got to do the same thing here too. So 25, because that's over 2, we're going to compute square root. So what's the square root of 25? 5, and then cubed is 125. So this would be 25 square root cubed. All right. So this is half, and then, 5 cubed minus 3 cubed. So half multiplied by 125 minus 27. Well, 125 minus 27 is 98. And then half of 98 is 49. Beautiful. Any question about this one? In the end, we could have done this one easily in 1 page. I took 2 pages because, I wanted to talk about all this stuff. Any question about it before we move on to a different topic? All right. So now we're in section 7.5, which is titled something like the area between curves. All right, so first remark is that the integral is often said out loud so it's often said to be the area under the curve. And I'm going to write under in scare quotes. So like this will, especially be the case if you're talking about this to, you're like engineering relative, right? They're definitely going to refer to it as the area under the curve, like very high certainty. So the reason for that is that the main reason anyway is that if we have given a function f on a to b such that, and this such that is the catch, such that f of x is greater than or equal to 0 on AB. Then that means that we're looking at a picture that's like this. A, B, and then, the way that I jokingly referred to this, several lectures ago, as I said, well, imagine this thing wants to go to the party, and it's going to put on its party hat. So then, its party hat is this, actually the graph of this function. So then, what does the integral have to do with this picture? It's the area. Yeah, it's this area right here. So the shaded area is the integral from a to b of f of x dx. And that's really, kind of an astounding thing, because, this shape is not like a circle or, all the other shapes that we learn in grade school. This is just some shape, right? It's like almost a rectangle, except I put a funny hat on it. And, as long as the hat has a property called integrability, then this is the formula for its area. Fine. Now, this is the kicker, right? Given an f, and really I mean an integrable f, on there such that this is the case, the shaded area is this. But what if the f is not always greater than or equal to 0? Okay? When f of x greater than or equal to 0 on AB is not true, then all that means now is that now I need to draw a function that is some of the time below and some of the time above. So if that's y is f of x, if that's the case, then this is why I have to, put scare quotes around under, because what in your own version of this sketch, please shade in the area that the integral is referring to. So is it like all this area down here? Nah, in fact, really what the integral is referring to, it's referring to the area that is between the function, the red, and the x-axis. That's what it's really referring to. Now, you can use the word under, and the word under makes sense as long as the red is entirely above the x-axis. But if it's sometime below the x-axis, then the under kind of, it's not really so good of a way to say it. So here, now it's talking about this. And to make things extra fun, is that the integral still has something to do with the area of these three regions, except now the integral is going to count some of the areas as being positive and other areas as being negative. So which ones are going to be counted in the positive sense? The ones that are above. And the one below is going to be accounted for negatively. Okay. So now you could ask, well, you could say, yeah, I fully understand that where the integral is concerned, this is accounted for negatively. But in fact, I just actually do have a shape that is shaped like that, and I just need you to tell me how much paint I need to paint it. Okay, that's what I need. So you're sort of telling me that, oh, well, you want to consider all of these areas to be positive, right? Because we're like using paint, you know what I mean? Like we're trying to actually get some work done. Okay. If you want them all to be reckoned all to be positive. So if you want all such areas to be seen as positive, then actually the thing that you want to integrate is not f. What do you want to integrate? So here's the thing. If you're telling me that, yeah, I've got a thing that's shaped just like that. I'm an artist, and that's what I do. And now I need to paint it. And you want to figure out just how much paint would it take to paint it? How much area does it take? Well, mathematically, can you agree that if I was to take this little negative region and then flip it up, that wouldn't change the area, right? If I was to just take it and just go and flip it up, it wouldn't change the area. So if I could make a new function that was exactly the same as this red one, but I just take this piece and just put it up there, flip it over, then we'd be good to go as far as computing the area. Well, what operation can we do to that function to make that happen? Absolute value. Then you actually want to integrate the absolute value of f of x, because what the absolute value does is, well, if that point is there and that point there, this one here and this one here, then what the absolute value will do is the stuff that's above the axis, it leaves it. It says, oh yeah, well, you're good to go. So that's like that, and that part's like that. And then the part that dips below the axis, it flips it back up. That's that's how it does its thing. So this would be exactly. And then this might be keeping track of how much money's in the register. But say, for example, that all transactions at this particular register were performed using the payment processor of Visa. Well, Visa's going to take a cut, right, of every transaction. That's how they do their thing. So then, as far as Visa's concerned, it looks more like this, right? Okay, fine. So you've got to be real careful about the area under the curve. That's a perfectly working analogy if the function is entirely positive. But if the function is sometimes positive, sometimes negative, you need to be careful if someone is telling you, you know, if they use the word under, you need to say like, okay, now wait a second. What do you mean? Do you mean like this one or that one? Okay, good.
So on a problem would it be?
On this, so, okay. On this, I think I take your question to mean how would I say when I mean this, and how would I say when I mean that?
Yes.
Okay, so then, if the language is something like integrate f over a to b, then this is the kind of thing that we're talking about. But if I were to show you such a picture, so if I was to produce such a picture for you right here, and if I was to say, find the shaded area, or find the area of the shaded region, which in not math terms, less mathy terms, would be like asking, well, how much paint would it take to paint this? Then you don't want to integrate this one. You want to integrate the absolute value of f, the one that looks like this. We're going to do lots of examples today, so that I think you'll, I think the should be clear, I hope.
We say find the area of the shaded region.
Mm-hmm.
So it wouldn't include the negative part?
It does, but this language, this is like the language that always means take a look at this shape, this weird shape that I've made, and reckon all of it to have a positive area.
Okay.
So that means that actually I'm not interested in you integrating f. I want you to integrate the absolute value of f. Yeah?
For the first picture,
This one?
yes, can you take the absolute value of everything so it's still get the same?
Yeah. The reason is because the function is always above the axis, right? So absolute value sees that all of these outputs are positive, and so absolute value is the same as doing nothing. So the issue that I'm trying to point out is that, you know, just be careful what the wording is. And the reason why is because today we're going to get big into calculating these. Okay?
So the simple way to do it is always including the absolute value.
No, I mean, yes and no. If we're talking about just the area of a shaded region, yes, absolute value.
That's the key. I mean, that's like what to look for is when you say the area of the shaded region. That
Yeah.
means that's
Absolute value.
Yeah, okay.
Okay, so then continuing that remark, now instead of the area under the curve, we can talk about the area between the curves. And just like under needs scare quotes, so does between. So now the story, instead of giving you half of a, 3 sides of a rectangle essentially, now I'm just going to give you 2 sides, and you know, Now this shape person wants to go to the party, so they're going to put on their party hat. But not only are they going to put on their party hat, they're also going to put on their party shoes. Okay, so what I mean is, here's yet another way we can make new shapes. So instead of just the top, us being able to choose what the top looks like, now we can also choose what the bottom looks like. Then the question is we want to find this area. We want to find a formula for it. All right. So please recall. So now I'm going to make a slightly easier to deal with version of that picture. What our definition of integral is we said, okay, take the shape, that you're so interested in, and then cut it into rectangles. So now I'm going to make the bottom just be a slanted line, but understand that it could be any kind of thing. We said, okay, we're going to take that shape and then we're going to cut it into rectangles. And then just for simplicity's sake, I'm going to cut it into 4 rectangles. And we said, after we cut it into these strips here, we come up with a way to make rectangles. And the way that we make them is we choose some sample points. Okay, so more or less what I'm going to do is either on the red or the green, it doesn't make a lot of difference. I'm just going to choose a point that's in each strip. So let's say that I choose like that point, and that point, that point, and that point. Okay, so because there are 4 strips, I made 4 choices. Then vertically, directly above each one of these, there's another point there. Now this isn't a choice, it's already been chosen, right? So I just take this one and just go all the way up until I hit on the same vertical line on the red, and on this one, and on this one, and on this one. So now, with each one of those blue dots, I'm going to draw a horizontal line through them in that strip. So like this. So there's 1, 2, 3, 4, 1, 2, 3, 4. Okay, so now we have 4 rectangles. And because they're rectangles and because we defined what that means, we can find the area of each one of them, and then we can add up those 4 areas, and that would constitute an estimate for the area of this shape. But it would just be an estimate. How could we make a better estimate? Yeah, more rectangles, right? And then the calculus point of view is that, well, let's just not stop, right? Let's just use infinitely many rectangles. Okay, but besides that, I'd like for you to consider. So for example, that particular rectangle that you can still see. Let's say, for sake of argument, that it has area 5. Okay, what about that rectangle? What's its area? 5, right? What about this one? 5. Because moving that rectangle around doesn't actually affect its area, right? So now, here's the thing. I hope you've had the experience of playing with a deck of playing cards. You know, you got to like shuffle them, and then after you shuffle them, you kind of like, you stack them to get them like, nice and lined up. I'd like for you to imagine that, maybe these are like really zoomed in views of playing cards. Imagine that I hold this one fixed right there. So I hold that one fixed. And then I take my little hammer tool and ding, 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 and I knock it down until it's exactly flat with that one, so that you know, this one and this one are side by side. And then I just continue doing that all the way down, like ding, 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 until they're all flat, you know? So to understand the consequence of doing that, let's say that this corresponds to some point C3, right? 3 because that's the third strip. And then the height, because this is y of g of x, y is g of x, and this is y is f of x. That means the height of that bottom point is y is g of C3. So the bottom is that value. And what's the top value? Right. So that's the individual heights. So maybe, you know, maybe this one's like at height 30, and that one's like at height 17. Then if that's the case, then what's the height of that rectangle if this top one is 30 and the bottom one is 17? 13, right? The difference between them. Right? Because if this one is at height 17 and this one 30, then that would be 13. So that means that the height of that rectangle has got to be the top one minus the bottom one, whatever those numbers turn out to be. So now, with this algebraic thing in mind, and with the playing cards, you know, lining up thing in mind, here I'm going to stack this nicely. Nicely. And it will end up looking like this. So now that we stacked it nicely, instead of this being a tilted thing, it's going to be exactly horizontal because we took the time to make it all flat. And then the effect of doing that, imagine that that also pulls the green down and the red down. When you pull it down, you're going to end up seeing a party hat that kind of looks like this, having pulled the red down. And then the rectangles themselves will end up, you know, looking like this. But then the question is that if we did that moving procedure, so notably none of these rectangles changed their area because all we did was just move them up and down, so those are all the same. But what's this function right here? Not quite though. Y is f of x minus g of x. But wait a second, this is exactly, you know, ignoring that that's what that looks like, this is exactly the kind of thing we already talked about, right? Okay, as a result, the area of this shape, of that one, is the integral from a to b of just f of x minus g of x dx. That's what it is. in the end, because you can just take all the little infinitesimal rectangles and just move them up and down. Okay, good. Now, be warned, okay? I put the between in the scare quotes, which is to say that, you know, if the functions cross, you've got to carefully figure out, wait, were they asking for the area or what? Right? Okay, good. So then there may or may not be absolute values somewhere, and we're going to do some examples where there are. Okay. So here's an example. Find, no. Let R be the bounded region bounded by y is the square root of x and y is x squared. So 2 requests. First request is give a sketch of R, and then 2, find the area of R. All right. So there's some required knowledge here, and that is you simply must know the domain and range of the square root function and the domain and range of the squaring function, and generally speaking, you have to know more or less what they look like. So to remind you of these facts, here we'll plot the square root of x, and on the other one, the squaring function. So what does the square root look like? Correct. So you start at the origin and then it goes up, kind of bendy like that. So that's what square root looks like, more or less. So now, well, how come I only drew on the right side? You know, what's wrong with the left side? Right, exactly. So the horizontal axis represents the inputs, and the origin is where the input is 0. To the right is where the inputs are positive, to the left where the inputs are negative. The reason why there's no plot over here on the left side is because it's not permissible to give negative inputs to the square root. Can't do it. So there's no plot over there. All right. What does the squaring function look like? Parabola. Okay, so it looks like this one. So what these, the fact of these, their looks and domains and ranges and things like that, that's assumed knowledge. So that means that we need to combine these and figure out what R it is that we're talking about. So to answer part 1, we're going to combine these. Into something like the following. So square root looks like this. And then the squaring function, something like this. All right. So now that we've got them on the same plot there, what is R? Yeah, this piece right here, right? So now let's kind of parse this language. So the bounded, so in the first place, bounded occurs twice, and that you know, where English is concerned, that sounds a little bit clumsy. You know, kind of like a sentence that only a mathematician could love. The bounded region. What that means is that we're talking about a region, a shape, that you could draw a circle around. That's what that means. So, like this bit right here, can we agree that I could draw a circle around it? Okay. Now, this region up here, you know, because this red continues going that way like that, and this green continues going that way like that. So, like the region that's, you know, that I'm sort of showing there, that's a region, right? And it's bounded on this side by the red, and it's bounded on that side by the green. But I'm not talking about this region. Why am I not talking about it? Because it's not bounded, right? Because this bit that goes that way, could you draw a circle around it? You can't, right? Well, imagine a very big circle. It's still going to go beyond that, right? Because it keeps going. This bit, right? That bit goes infinitely far that way. So every circle that you could conceivably draw, it would go beyond that. So this region is not bounded. You couldn't draw a circle around it. In fact, there's only one bounded region. It's that one. And then bounded by, that means that, well, considering that region, the edges, the boundaries must always be either from the red, from the green, or from both.
That's the region stay the same, no matter how big the
Right, yeah. So this here, that's R. Okay, so any question about the answer to part one? All right. So then for part two, we want to find the area. Of R. So this means, you know, how much paint would it take to paint R? Well, so in order to do this, we need to turn this into, well, let me ask it like this. I'll say this first. We need to use the formula integral a to b of f of x minus g of x dx. So that's what we're going to use because it's the area between two curves. So we're going to use that. And then the first question I want to ask, will it be the square root minus the square? Or will it be the other way around? X, the square minus the square root. So, which one? Square root first. Why? It's on top. It's that simple. Is that the red one is the one that's on top? So that's the one that we're going to do. Because if you do red minus green, that's going to be a positive value. If you do it the other way, it'll be a negative value.
Take the absolute
Yeah, you can. But this consideration that we're making right here is more or less saying, how will we use the absolute value? Will it end up being that one? Or will it end up being that one? But same consideration. So it will be, it's always going to be top minus bottom. And therefore, the answer to this question is it's going to be the square root of x minus x squared. Okay, next question is what is the interval AB? So we need to figure out, we've determined, okay, we're going to integrate something, and the thing we're going to integrate is square root x minus x squared. Then furthermore, because we're integrating, we need to know, okay, what interval are we going to integrate over? Okay, well, in the picture, you know, here's a particular x. It's a negative x, you know, like maybe like a negative 4, I don't know. Do we need to be integrating over here? No, because that's not, these x's don't have anything to do with the region. What about over here, like at x is 10? Do we need to be integrating over here? No, right? We need to integrate from here to there-ish. So specifically, if you can imagine that I have a flashlight, and it's shining onto that thing there, and it's casting a shadow on the x-axis, that's where we need to integrate. Right. So specifically, that's the interval we need to integrate over. So we need to figure out, okay, what's that interval? So we need to find specifically the way that we're going to go about doing it. The thing that makes these two these important are the fact that that's where the red and the green are intersecting. Right? You can see that the red and the green intersect there, and the red and the green intersect there. So we need to find the intersections of y equal the square root of x and y equal x squared. Okay, so we've got to find the intersections. So then, you know, if it were just as simple as that, like on plotting paper, you kind of just use your human eyes and do it, but it's not that simple here. So when you want to find intersections, what does that mean? What are we going to do? Like mathematically, algebraically. Yeah, we need to solve an equation. So therefore, we need to solve the equation. So that is to say, we want the x's and y's to be the same. So because we want the y's to be the same, that means that the two right-hand sides must be the same. The square root of x must be x squared. So we want to solve the equation square root x is equal to x squared. Okay. And from here, I'm going to drop the color thing. I'm just going to write in pencil now, because I hope the correspondence is clear enough. So how can we solve this equation? Okay. So I take it to mean, maybe I'll move this one over there. So 0 equals x squared minus square root x. Okay, now what? So like, just like any, teaching is a profession, like a calling, I would say. And any professional group has like the language, that they speak, like the special jargon. And part of the cynical jargon of teaching math, part of the cynical phrases that we say is that calculus is where they finally start to learn algebra. All right? And, the course that comes after calculus is differential equations, and so differential equations is when they finally start to learn calculus. And that's a little bit cynical, but it's also a little bit funny because it's a little bit true. Right? So then we're asking how to solve an equation. And notably, on this page, no calculus whatsoever has occurred. Like, the only calculus-y thing has been that we've acknowledged that eventually we're going to do this, but no actual calculus operations have occurred yet. So, all right, this is an okay place to start. Let's to kind of nudge you slightly in the right direction. I'll say, okay, I'll represent this as this square root as fractional exponent half. And so, what if, as an aside now, what if you were solving an equation that looked like this? Say 3 times x squared. Let's make that to make it slightly easier on the eyes. How about 3 times x to 4 minus, say, 6 times x squared equal to 0. Then what would you do? What would be a good idea? Yeah, we can factor out a greatest common factor, right? So as for the coefficients, I can see that 3 is common to both. So we could factor out a 3, and we could write that this is 3 times x to 4 minus 2 times x to 2 is equal to 0. And then what can we do? We can factor out whatever the biggest power of x is, right? Or whatever the biggest possible one is. So how much x would we factor out? X squared, so that we could do 3 x squared, and then this would leave x squared minus 2, like that. And then, we could go on from there. So this is a nice place to be because now, I'm covering up something. We have one thing, 3x squared multiplied by another thing, and then it's all equal to 0. And the thing about the reals is that if you have a multiplied by b is equal to 0, then one of them's got to be 0, right? That's one of the neat things about the reals. And so then from here, the possibilities would split into 2, where you'd say, well, one possibility is that 3x squared is 0, and the other possibility is that x squared minus 2 is 0. So either that one is 0 or that one is 0. So this is just an aside. Now, this one that I gave you is easier than where we are now, only because I made the exponents be integers. But it's the exact same story here. Notice that we've got some x to some exponent, and we've got x to other such exponent. That means that we can factor out x's. How much x is supposed to come out? X to half. Because it's what you do is you take all of the choices, right? If there were like 10 choices, so like here again there's 2 choices, 4 and 2. You always choose the one that's least. 2 is least. So that's how much comes out. Here the choices are 2 and half. Which is least? Half. So half is what comes out. So this would be 0 is, well, let's see if we can figure out what's supposed to go in there. We're saying that half is what comes out. Half is what comes out, so what is it that we're supposed to put in there to make it come out right? So continuing that over here. So if we took out half, out of all of it, what becomes of this? Just a 1, right? So this would be minus 1. And then what becomes of that one? 3/2. And how'd you get that? Yeah, you subtract, right? Because from here to here, from here to here, we took out x squared. So what did you do with the exponents? Well, you subtracted 2, right? 4 minus 2 is 2. 2 minus 2 is 0. All right? So this would be x to 3/2. X to 3/2. The reason why this is x to 3/2 is because when you factor out, x to any exponent, you subtract n from all exponents. Therefore, that exponent it was a 2, and then we're subtracting half. And, well, 2 is 4/2. 4/2 minus 1/2 is 3/2. Good. Finally, or not finally, but moving on, we have a multiplied by b is 0. So what must be true? One of them has to be 0. So therefore, the possibilities split into 2. One possibility is that x to 3/2 minus 1 is 0. The other possibility is that x to 1/2 is 0. One of those has to be 0. So now this one's pretty easy now. The reason why this one's pretty easy is that it's asking what x has the square root of x is 0. Alternatively, you can take this and you can move the exponent to the other side. So when you move the exponent to the other side, that means that the x stays still, the 0 stays still, but this moves over here. And what does it become when it moves over here? No, it doesn't just move like that. When it moves, it changes. It becomes square, right? So moving. Yeah. So what's 0 squared? 0. Similarly, for this one, we could move the 1 over, and then we have the equation x to 3/2 is 1. And if we want to get the x by itself, then we take the x, leave it still, take the 1, leave it still, and we want to move the exponent over. And when the 3/2 goes over to the other side, what does it become? 2/3. It's reciprocal. And then, well, what is x? What is 1 to 2/3? Well, it's 1. You could say, well, what's the cube root of 1? It's 1. And then what's 1 squared? It's 1. So there's 2 solutions. I claim that that is entirely expected. Why is that entirely expected? Because there's 2 intersections. One of the things that I want to, repeatedly remind you is that these intersections are in exact correspondence to these solutions. The fact that there are 2 solutions is entirely expected, assuming that we were even close to right about the picture. There's 2 intersections. There's 2 solutions. All right. So these intersections are telling us something. They're telling us that the picture, if you zoom in on it really close, or just draw a nicer looking version of it, I suppose, the picture really looks like this. We know that this here is x is equal to 0, and this is x is 1. So, therefore, the area of that shape is what? How do we write it? Uh-huh.
X squared minus. Oh, I didn't read it.
So let's look at it real quick.
Square root of x minus.
So which one's it going to be, and why?
Square root.
Because it's positive.
Right. We need it to be top minus bottom. We need to do the. We need to choose the positive version of the difference. Is it going to be that one or that one? It's going to be that one because that's the positive one. Because it's going to be, we need it to be positive, so top minus bottom. So like so, square root x minus x squared. Okay, so now let's take stock for a moment. Again, no calculus steps have been taken. We haven't done any derivatives. We haven't done any antiderivatives. We haven't done anything. All that we've done is we remembered that integral is related to area. And what we've done is we've performed some algebraic and geometric considerations to say that, in fact, the area of this region R can be determined by calculating this integral here. But we still haven't done any calculus yet. That being said, if this exercise were out of 10, then successfully getting to about right here would be like 7 or 8 of the points. The rest of it is honestly a really straightforward application of the fundamental theorem of calculus. And it's only going to be worth like 2 or 3 points. So that being said, I'm going to do the rest of it like real quick because that's the boring part. Is there any question about how we got here? Because the conceptual part is like, in a real sense, that's what you're paying for, right? That's what you're paying me to teach you, yeah?
So if, let's say, the integral of 0 to 1 and you switch to x squared minus square root of
Mhm.
x, then the two numbers, are they going to be the same except for the negative?
Except for the negation, yeah.
Oh, okay.
But the thing is that if you do that, you won't get full credit, right? Because you might say, well, I'll do it however I want, and then if it turns out to be negative, then I'll just negate it. No, that's not going to fly. Yeah?
If you found the integral from 0 to 1 for square root of x and then subtracted the integral from 0 to 1 to x squared, you just did them separately in this
Yeah.
guy. Are there cases where would that most of the time be more difficult than finding like one equation or one function?
No, it'd be more or less identical.
Yeah.
It'd be like the same amount of work. In the end, the integral is additive, which means that if you so wished, you could say that, well, I'm going to integrate that one by itself, I'm going to integrate that one by itself, and then after I've done that, I'm going to subtract. It'd be just fine. It'd be about the same amount of work. Okay, so that being said, well, we want to use the fundamental theorem. Do we know the antiderivative of this? Yeah. So this one uses the power rule with exponent half, and this is the power rule with exponent 2. So then this would be, so x to, since that's half, and then half plus 1 is 3 halves, so this will be x to 3 halves, and then divide by 3 halves, and then subtract x to 3 and then divide by 3. And then this all evaluated from 0 to 1. And then those endpoints are like gifts, right? Because these things couldn't be any easier to evaluate than at 0 and 1. Okay, so then just carrying that out quick. So that would be something like, well, 1 to 3 halves, divide by 3 halves, and then minus 1 to 3 over 3, and then subtract just a big 0, because all those things evaluated at 0 is 0. 1 to 3 halves is 1, and then division by 3 halves is same as multiplication by 2/3. So this would be 2/3, and then minus 1/3, and then minus 0. Just writing the 0 again to help your eyes follow what it was that I did. And then 2/3 minus 1/3 is 1/3. So what is the meaning of that number 1/3?
The area of the dot.
Yeah, it's the area, it's that area right there. So, you know, if this was measured in feet or something, then what this 1/3 would mean, it would say that, well, if you're going to paint that thing, you need to buy enough paint to cover 1/3 of a square foot. That's what that means. If this was miles, well, then you'd have to buy enough paint to paint 1/3 of a square mile. Do you have a question?
Yeah, just to be clear, so it's like we were saying with the flashlight, that's the area we're finding out the shaded area that you have in the graph. That's fine.
I didn't follow you?
Okay, so the 1/3 is the spot, like when you said it makes the shadow, like you're doing a flashlight on top of it.
That's the interval.
Oh, that's right, and then the area with the pod-looking thing is the 1/3.
Right. Yeah. This. Yeah. What I'm saying. What I'm saying is that you know, the shape looks like this. Ish. This has a area 1/3, and then the interval that we integrated over to make that determination was the interval 0 to 1. Other questions? All right. So much fun. Let's do another one. Where are we? Okay, so then find the area. Again, so let R be the region bounded by these things, bounded by what? What am I looking for? This one. So by x is 1, x is 6, y is half, and y is 1 over x. And of course, let R be the bounded region. Bounded by. Blah blah. So in order to make sense of this, again, you just must know what each one of these things look like. So please recall. I'll just do 3 of them. So what does x equal to 1 look like? Vertical line at x is 1. Not complicated. X equal to 6 is just like it, except it's over there at 6. What does y equal to half look like? Horizontal line at height half. Okay, and then what does y is 1 over x look like?
Really slowly diminishing.
Away from the origin, yeah, it's doing that. What about near the origin? In fact, we talked about this last time.
There it goes again.
Yeah. So it looks like this. And by the way, so if you're hesitating on the shapes of these things, you know, please let that serve as notice to you that it's just expected that you know what these things look like. So meaning that it would be perfectly legitimate for me to give you a quiz exercise and for you to just expect you to know that this is what it looks like. This shape is important enough and common enough to have a name. Its name is hyperbola. And if that sounds like parabola to you, then very good. But it's obviously not a parabola. But they are related to each other. Parabola, hyperbola, circle, ellipse, and a few other examples are things called conic sections. Good. So we need to, you know, sketch. We want to sketch the region R, you know, because it's the same instructions as before. So the first request is for you to sketch the region R, and then the second request is find the area of R. So to satisfy part one, we need to figure out, well, what does it look like? Okay. Well, concerning this red is always at height half, and this green is always at, well, none of this green down here is ever going to touch the red, right? So they're never going to, like this green down here is not part of it. So ignore it for a second. And then you can see that this part is way above half, and it goes down, 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 and gets as close to 0 as we want. So it must eventually cross half. So what I mean is that if we were considering a plot where the red and green were both present, where would they intersect? So we want to find, that intersection.
How about the x and 1 and x and 6? You include
Well, we're going to need to figure that out too, also. But before I even deal with those, I want to know, you know, where is that? Because the thing is that 1 and 6 could both be over here. They could both be over here. They could be straddling it. You know, where are they is the question.
on the left.
So x equal 1 and 6 are both going to be over here? Well, we'll have to see, right? The question is are 1 and 6 like here and here? Or are 1 and 6 like here and here? Or are 1 and 6 like here and here? You see, we don't know where they are. So we want to find that intersection. All right. Because this is y is half, and because this one is y is 1 over x, then finding the intersection of two plots always means the same thing. What does it mean? Yeah, we need to solve an equation. So therefore we need to solve half equal 1 over x. All right. So how do we do it? Yeah, x equal 2 is the only solution. You know, maybe that's obvious to you. But alternatively, we can compute the reciprocal of both sides. right? Reciprocate both sides so that the equation now reads 2 over 1 is x over 1. Okay, so then x is 2. Okay, so any question about that? So that's important to us because that tells us where the 1 and the 6 are, right? So we haven't considered about x is 1 and x is 6. But because the intersection occurs at 2, that means that the 1 and the 6 are on either side, instead of both being on one side or both being on the other side. So therefore, the equation, the plot looks something like this. Blah, blah. So this. 1, 2, 3, 4, 5, 6. And then I could say that, you know, this is like 1, 2, 3. So 1, 2, 3, 1. So that means that it looks like this. So the 1 and the 6 are interesting because that was in the initial description. And the 2 is interesting because that's going to tell us where an intersection is. So y is half that. And then the hyperbola. We'll do something like this. So it comes down, crosses, and then something like that. It continues going this way like that, but we're not so interested in that part. Or that part. So what's the area that, what's the region that we're talking about? So remember, it's the bounded area, bounded region, which is bounded by these things. Mm-hmm. Well, it has to be bounded by, each little bit has to be bounded by these things and not other things. So specifically, like, well, here's one. That's part of it. Okay, can you see anything else? Yeah, like this. So that's the region. And here's the thing. We want to find the area of region R, which is the same as asking, you know, how much paint would it take to paint it? Right? So, well, here's the thing. Look at this left bit. Would we do red minus green or green minus red for this one, for the left one? It'd be green minus red. And what about for this right piece? Be the other way around, right? So that's the answer to part 1. So the answer to part 2, to find the area, well, we can see that what we want to do is we want to integrate from 1 to 6. That's what we want to do. And it is going to be absolute value. And I'm going to write it like this. It's kind of an abusive notation, but I think you'll take my meaning. So green minus red. So the absolute value of green minus red. But the thing is that some of the time it needs to be red minus green, and the rest of the time it needs to be the other way around. So we need to split this integral into pieces. What pieces do we need to split it into? 1 to 2. So it'll be the integral from 1 to 2, and then dropping the absolute value. Should it be, in 1 to 2, should it be green minus red or the other way around? Green minus red. So it'll be green minus red, like that. And then we'll want to integrate also from 2 to 6, the other piece. And then what will it be there? Red minus green. So I hope that you understand why on Tuesday we worked so hard on the absolute value business. It was so that today would be slightly less painful, so that instead of trying to juggle 5 balls at a time, we're just juggling 4. So, is there any question about conceptually getting to here? Of course, I'm being kind of silly writing, you know, green and red. Of course, what I mean by that is integral 1 to 2 of 1 over x minus half dx, and then plus integral 2 to 6 half minus 1 over x. So is there any question getting to this place? Because again, if this exercise were out of 10, to the present position, we're talking about like 8 out of 10 points. The rest of it is honestly a little bit boring. Yeah?
For the area, why is the bottom one doesn't count?
Which bottom one?
Well,
Down here?
yeah.
Well, except for, okay, let's write it like this. So that is, this picture looks like this. Ignoring the axes for the moment. So just drawing a picture where the axes aren't present, the picture would look like this, like so. Okay. So then, because it needs to be bounded by these, there can be nothing over here to the left of x is 1, and there can be nothing over there to the right of x is 6. Okay. So I think your question is like, why are we not including that much?
Yeah, from 1 to 5
Like this stuff down here?
Yeah, yeah.
Well, because if we were to do that, if we were to continue drawing the green going this way, say, and that way, like that, and the red going this way, then you're asking about this region going down. So this bit going down, how far down does it go? All the way down, right? There's nothing stopping it. So this bit right here does not constitute a bounded region. Right? You can't draw a circle around this thing. So we're not talking about it. Whereas that piece is bounded. You could draw a circle around it. And that piece is bounded. You could draw a circle around it. But like this piece that's going up that way, it's not bounded. This piece going up that way, it's not bounded, etc. So does that answer it? Okay. So then from here, this is just boring, so I'm just going to just crank through it. So this would be log absolute x minus half x, evaluated from 1 to 2. Plus half x minus log absolute x, evaluated from 2 to 6. So that's just so that's a straightforward fundamental theorem of calculus. And then now plug stuff in. So that would be log of 2 minus half times 2 is 1, and then minus log of 1 minus half times 1 is half. By the way, what's the log of 1? 0. So then this would be plus half of 6 is 3, and then minus the log of 6, and then minus half of 2 is 1, and then minus the log of 2, like so. And on such an exercise, I would probably say, simplify it and give me the exact answer if it turned out to look this way. So I'll go ahead and do that. So we want to distribute all that. Of course, that's a 0, log of 1. And then we're doing log 2 minus 1, and then minus negative half. So that's really plus half. So subtract 1, add half. So subtract half. So that'd be log 2 minus half. And then plus, well, that'd be 3 minus 1, so that'd be 2. And then negative log 6, and then minus negative log 2. So that's really log 2 minus log 6. So that'd be plus log 2 minus log 6. Okay, then simplifying this stuff, I can see that we have log 2 plus log 2. So that'd be 2 log 2. And then minus half plus 2. So that would be, well, let me deal with this log 6 here. And then minus half plus 2 would be plus 3 halves. And then the log thingy, like if this were a MyMathLab exercise, if it were a MyMathLab exercise, then they would go on. So in particular, this can be simplified, 2 log 2. How can it be simplified? It can be simplified to log of 2 to exponent 2, like that, because this 2 that is out front can come inside the log and become an exponent, like that, because the rule that was used there is that a multiply log b is the log of b exponent a.
Is that log of 4?
Yeah, 4. Well, I mean, I wrote 2 to 2 just so you could see where the 2 went. Yeah, I'm going to write 4 in a second. Then minus log 6, and then plus 3 halves. So, of course, that's log 4 minus log 6. But again, if this were like a MyMathLab exercise, then MyMathLab would simplify it further to what? Well, maybe not, like if it was going to give you the exact answer. So you can do something with this. Yeah, you could say that this is the log of 4 over 6 plus 3 halves. Because the rule that was used here is that the log of a subtract the log of b is the log of a divide b. And then, 2/3. The log of 2/3 plus 3 halves. So I'm just showing you these kinds of, arithmetic dance, because that's the kind of thing that comes up sometimes. Any question about it? All right, let's get another one going. This is okay? All right. So now I think it would be informative, I hope, for you to see just how I might make an interesting exercise. So let's make one. So this is a hidden block, something that you would not, under normal circumstances, see. So I want a parabola with two integer zeros, which is to say that, I want something that looks like this. I want a number line. I want to pick two integers. I want a parabola that goes through them. I'll make my life easy and make it open up instead of down, because otherwise I'd have a negative floating around somewhere. Now, just to be quick, I'll go ahead and say that the numbers are 3 and 8. Those are the zeros that I want. And one of the things that you need to take from college algebra is in fact called the Fundamental Theorem of Algebra, which says, among other things, every polynomial must have at least one complex zero, and furthermore, all zeros are in correspondence to factors. So the fact that 3 is a zero means what is a factor? Not quite. Because if 3 is a zero, then x minus 3 must be a factor. And similarly, because 8 is a zero, x minus 8 must be a factor. And then to make the later calculus bits easier, I'm going to multiply by 6 in the front. So now I'd like for you to observe this expression here. What would you get if you plugged in x equal to 3? 0. Right? That's the whole point. And what do you get if you plug in x equal to 8? 0. And in fact, 3 and 8 are the only x's that you can plug in so that you would get 0. All right, carrying this out, 6 multiplied by x squared minus 11x plus 24. And distributing the 6, 6x squared minus 66x plus 144. I'm going quick because I'm up against the clock. So now I'm going to take any line. So I'm going to pick some line here, and some line like this. And this bit is actually far less crucial. So I'm going to say that the line that I choose is y equal to 13x plus 26. Ha ha ha, right? How many times can I get 1326 to show up in the semester? All right, then what I'm going to do is I'm going to do this plus this. Add those together. Doing that, I see that we have 6x squared, and then adding those together, minus 53x, and then adding those together, plus 170. Okay, and again, here you're watching me make an exercise. Okay, that's what we're doing here. Now here's the exercise. Let R be the bounded region bounded by x equal to 1, x equal to 10, y equal to 13x plus 26, and y equal to 6x squared minus 53x plus 170. And then the same instructions as before. Sketch the region R, find the area of region R. right? So again, what these things look like, it's assumed knowledge that what you know what these are. So if you were to plot 13x plus 26, what would it look like? It'd be a line that's sloping up. And what would this look like? A parabola that opens up. So now, in your mind's eye, imagine a parabola that opens up and a line that slopes up. And we need to consider how many different ways could they intersect or not. There's three possibilities. So concerning one, there's three possibilities. One of them is that the parabola looks like this, and the line cuts through it twice. That could happen. But I could move the line down, and if I move the line down to just the right place, then those two intersections will actually collapse into a single intersection, and it'll look like this. Of course, such a line is called a tangent line. If I move the green line down any further, then they won't intersect at all. So what we need to do is we need to figure out which case are we in. So how do we figure out which case we're in? Yeah, we need to solve an equation. So to determine which of these we need to solve the equation that is red equal green. Okay. So I need 30 more seconds so I can get to the punchline. So doing that, that would be 6x squared minus 53x plus 170 is equal to 13x plus 26. Now, if we want to solve this, we need to get one side equal to 0. Okay? So then subtracting this right-hand side from both sides, we'd have 6x squared, and then how much x? 66x. And then how much constant? 144 equal to 0. And then we need to factor this. And I can see that, 6 is a common factor. So that'd be 6 multiplied by x squared minus 11x plus 24. And then that quadratic in parentheses, does it factor? It does? How does it factor? Incredible. So that means, what are the solutions to this equation? Right. So that means that we know what the picture looks like. Which one is it? It's got to be the first one. Two solutions, two intersections. So the last thing, so that we don't go the whole weekend without the answer, is that the picture looks like this. So the picture looks like that. And where is this point? Where is this? That's at 3. And where is this one? At 8. And then now you've got to remember, where were we integrating from and to? Or where were we, we were also interested in these, is what I'm saying. Yeah, so then x is 1 is over here. X is 10 is over here. So what's the region that we're talking about? Yeah, so then we've got this piece here. We've got this piece here. And this piece here, yes. And as a result, for 2, we'd want to do the integral from 1 to 10 of the absolute value of red minus green. But of course, this would need to be split into how many pieces? 3 pieces, right? So then this would be the integral from 1 to 3 of something, dx, plus the integral of 3 to 8 of something, dx, plus the integral of from 8 to 10 of something, dx. And what goes in each one? So what goes in the first one? Right, red minus green for this one. In the middle, green minus red. And in the right, red minus green. And then from here, it's just a really boring application of the fundamental theorem of calculus, right? Each one of these is a polynomial, a polynomial, a polynomial. You use the power rule a whole bunch of times. You evaluate a bunch of polynomials at a bunch of different points, and do a bunch of really boring arithmetic. But again, getting to this place is like 8 out of 10 points. Okay, I hope you have a wonderful weekend.